What's up, everyone? It's Calc time with me, Miss Wesley. It is good to be here. Today, it's an exciting day. We get to our final section of this unit on limits that we're talking about at the beginning of calculus here. And we'll start this section today. I want to walk you through some notes on the beginning of 1-6, and then know that we'll have time in our next class to ask questions and do some practice on it too. So please join me on page 29 of your limits packet where it says limits at infinity. And I want to look at the bottom. I want to start at the bottom of page 29 with this example you see with the graph here. I like to start things off on a lighter note, so here's a joke for you. What would you call a guy who does his math out on a sunny day on the beach? Well, you might want to call him a tangent, because he's getting a tan. He's probably a gentleman, and tangent, trigonometry. Feel free to use that joke on your friends and family. Let's see what this question is asking. We've talked about limits for a while now, and we've looked at graphs to find certain limits. Imagine if I were to ask you, find the limit anywhere along this branch of the hyperbola, or anywhere along that branch. On those branches, like say a limit at x equals 1, it's not too hard to be able to just look at the graph of the function and find the y value that's being approached from the two sides of that x value. So I could ask for all those limits. I could even ask for a limit at x equals 0. It's just you'd probably tell me that there is no limit because from the two sides you're approaching a VA, so there's a break in the graph. But one thing that we haven't focused on are the two far ends of the function, and that's what we start today. These are called limits at infinity. So the weird part about what I'm going to write is we're so used to having x approach a certain value, like a number that's within the domain. Now I want to talk about x increasing without bounds. I want to find a limit as x approaches infinity for this to answer that first question of f of x. And you know what? I can visually, answer this question the same way I would have answered a question about a limit anywhere along that function. Go ahead and look at the graph at the far right end and see what y value is being approached. It looks like the graph is approaching 1/2 the value of the asymptote. It's the horizontal asymptote, the HA, that we're referring to here. Just that dotted line right across the screen that it looks like the graph is getting really close to as x gets bigger and bigger and bigger. So the HA kind of helped me with this first infinite limit. Keep that in mind. What about another infinite limit? I also circled the far left side of the graph, and it seems like I could put that same answer. I could put that same y value as being approached to the far left side. So keep this concept in mind, horizontal asymptotes, which is really a pre-calc topic from earlier mathematics, and see if that makes a lot of the questions we do on the next page a bit easier, quicker, and more convenient. So I'm going to flip over to page 30 and just fill out some vocabulary at the top, that a limit at infinity really just means it's a limit, right? So a number like L1 or L2 that's approached as x either increases or decreases without bound. You know we're talking about infinite limits here because for each example, I see x arrow and some sort of infinity. So we'll call those limits at some sort of infinity, so at infinity. Okay? And trust me, we will get rules for these things and we'll get strategies to make solving problems like 1 through 6 a lot quicker. But before we get there, it's always good to explore and kind of relate a new topic to what we know already. And here's what we know already. Let's look at number 1 together. Y equals x squared. We're pretty familiar with the graph of y equals x squared. So familiar that you could probably sketch a graph or think of one in your mind without having to pull out a calculator, that you're thinking of that parabola. And we want an infinite limit. We want the limit. We want to know what's happening as x is approaching infinity. Well, in this one, from the equation and from the graph, as x gets bigger and bigger, I believe y also gets bigger and bigger. We could either say the limit does not exist, we know that's a true answer, or we could say that the graph approaches infinity. And we could think about that by looking at x squared as well. Imagine plugging in larger and larger numbers for x. 1, 2, 3, 4, 10, 20, 40, 80. As x gets bigger, x squared is also going to rise. Would the same thing happen in number 2? Imagine, just plug in, imagine what's happening as x gets bigger and bigger. 2x should go to infinity, right? I should be plugging in, be drastic, 100, 1,000,000, 1,000,000,000, and you're doubling it. The -1 is going to kind of stay. It's not going to change. But I'm wondering how important that -1 is to the answer. And I don't think it's very important. I'm going to say infinity minus 1 let's just call it infinity. Let's keep it simple like that. And I want to relate this to monetary terms. They say money talks. So if X is the amount of money you have, and picture somebody giving you large sums of money, a million, a billion, a trillion. I'm a trillionaire, and they're going to double my money. Am I really going to care if someone walks up to me and asks me to borrow $1? Is that going to impact me financially very much? And in the grand scheme of things, it's not. As X grows without bound, that -1 becomes trivial, and this thing is also. This is a line if I were to graph it, and it just rises forever as X rises forever. What if the X, like in 3 or 4, what if you see an example where the X is in the denominator, where the denominator rises forever and ever, but the 1 is going to stay a 1? Picture 1 over 100, such a tiny little decimal, 1 over 1,000, 1 over 1,000,000 and 1,000,000,000, right? You're getting these tiny, tiny decimals really close to what whole number? And I'm wondering if you're thinking 0, that this whole entire fraction will just go to a tiny decimal that's close to 0. We could also confirm this with a graph. If we think of the graph of 1 over X. As X gets bigger and bigger and bigger, the graph is going to get smaller and go towards 0. Feel free, as I'm talking through this, to pause, rewind, right? Take it a little bit slower. If it seems like we're racing through these a little bit, trust me that we'll have a strategy once we go through the steps at the bottom of this page, where the answers, I think, will come quicker to all of us. What about 4? Right? We've got a 5 that stays a 5. There's no helping the 5. That's going to stay. But how about this fraction? 2 over large sums, bigger and bigger, right? 1,000,000, 1,000,000,000, and they're squared. This whole thing's going to go to 0, just like the answer to number 3. And for that reason, you could say this limit is going to be 5, right? The 5 stays. The other fraction kind of wastes away. For number 5, don't be shy about this exponential expression. Think of what dominates this function. The 3 is going to stay put. It's just going to be a 3. But e to the x is going to be some drastic exponential growth. E is that constant. That's 2.71828, and it's being raised to bigger and bigger powers. You've got 3 over a huge sum. I'm going with 0 yet again. And then how about 6? Watch out for something like this. And again, we'll get some rules underneath. But you have x going to negative infinity. I wonder if this is a case where it's going to make much of a difference. You've got the 7 that stays a 7. The 1 over x, well, it's 1 over lower and lower negative values, but minus 1 over negative a billion, 1 over negative a trillion. This whole thing's still going to 0, no matter which way you slice it. I guess I could say -0, but either way, you're left with a 7. I'll put a ... there. I feel like this is the part where if I'm going to solve, as I look down the page, number 6, 7, and 8, I really want some rules to stay organized about this. And before we move a step further, let's travel straight to the bottom and relate horizontal asymptote rules to strategies for finding infinite limits. Because I don't know if you noticed, I was getting answers like does not exist, 0, or sometimes I got a constant whole number. And those with rational expressions, those relate to these rules that we got in a previous math course for finding horizontal asymptotes on the graph of a rational function. You'll recall the line y equals L is a horizontal asymptote. Of the graph of f when its infinite limit is L to either the far right or the far left of the picture. And we might as well have these rules in a convenient spot since it's been a while since you've used them. So let's refresh them. If you recall, finding HAs on a rational function involved comparing the degrees of the numerator and the denominator. And I always like to say you're in one of 3 cases. Either you're in a bottom-heavy case where the HA is always 0, degree is greater on the bottom, or you're in a top-heavy case where there actually was no HA. The limit at infinity, just like the HA, is not going to exist. It'll be none. And then there was this balanced case where the degrees were the same. If that ever happens, we make a fraction. Your HA and your infinite limit is going to be the ratio of the leading coefficients that you see on the fraction. And I'll demonstrate that we don't have to show a lot of work for these with the 3 examples that you see above. Okay, so you can always pause here to finish copying that part. I want to look up at number 7. So 7 says, okay, we got to decide. Can you actually go through 7, 8, and 9, pause the video, and just write down the case that you think you're in? Decide top heavy, bottom heavy, or balanced. So I'm going to say higher degree on bottom, bottom heavy for this one. I'm going to say, ooh, degrees are the same for this one. So this is a good example of the balanced case. And then how about followed by a top heavy, higher degree up top? It's funny how the circled term really dominates the fraction if you think about it, and it's the only important term or terms involved. It's like the others are gonna kind of drop out. So I got to remember the answers. If I think back to the rules, bottom heavy was always 0. So I'll say here the limit as x approaches infinity of f of x for this one is going to be 0. Just because you're bottom heavy. That's a nice, easy solution. And look, I didn't really have to show work to get it because I knew what case I was in. How about for 8? The limit as x approaches infinity of f of x is going to be balanced. Let's pull off leading coefficients. So -2 up top and a 3 on the bottom. And top heavy. If you remember what we wrote at the bottom, top heavy was the case where there is no HA and there is no infinite limit. I picture the top as just increasing or decreasing so much quicker than the bottom. It just can't catch up with it, and you're not limited off. We'll say DNE, which we know can be written as some sort of infinity in many cases, a positive or a negative. And I think this will sink in nicely if we turn the page and try some practice examples. Let's see where we could utilize these cases, the top heavy, bottom heavy, and balanced on page 31 to make this not a lot of work for us. See if you can try. Pause the video and try 10 all the way through 13. And then let's pick it up after that. So when you come back, check these solutions for me. I'm thinking top heavy, so none, DNE. I'm thinking bottom heavy for this one, and it's an infinite limit. So bottom heavy, we'll say 0 always. And how about balanced? Leading coefficients, 3/5, and maybe another top heavy. I know it feels like we kind of raced through those, but you're using the HA rules. You're using the cases because you see that it's an infinite limit. Top heavy, bottom heavy, or balance can make those a lot quicker. I actually love these problems because they involve showing less work than the limits we had to find earlier in the packet. 14 and 15, a little bit different. You have a negative infinity there, and I just want to point out that sometimes the negative infinity is going to affect the sign of your answer, and sometimes it won't. If you know that 14 is bottom heavy, and you know you're looking for 0, it actually doesn't matter that the bottom's getting increasingly more negative. 0 and -0 are the same exact thing. So still a 0, no matter way you slice it for 14. But what about 15? In 15, we're balanced, right? X to the 5th and x to the 5th. I want to say my answer is some sort of 3, like a 6/2 for those leading coefficients. But I'm wondering if that sign's going to affect things. So really picture what's happening in those two circled terms. I would say the numerator is getting increasingly more negative. You've got negative numbers plugged in for x to an odd power. But I would say the same thing about the denominator. Here's the only important term in the denominator, and again, a negative to an odd power, getting increasingly more negative. We're going to keep this answer as a 3. We're going to leave it where it is. But can you skip with me down to 20 and 21? This is where I want to end things for today. In 20 and 21, it's the same question, once with a positive, once with a negative infinity. 20, this is a tough one, is actually balanced. It doesn't look like it. It looks like it's top heavy, but the squared is inside of a square root. This gets treated like square root of 2 times x to the 1st. So we are balanced. I'm going to say square root of 2 is your leading coefficient up top, and a 3 is your leading coefficient on the bottom. Now to finish it off, if x approaches negative infinity, I would say still my answer is balanced, square root of 2/3. But look, the bottom's getting increasingly more negative as you plug in lower and lower negative values for x, but the top is not. As I plug in lower and lower negative values for x, the top stays positive because this thing is squared and under a square root. Here's one case I just wanted to try and squeeze in where your answer changes to negative. We will get more of a chance to practice with this in the coming days. I just wanted to try to take some initial notes and start to relate these questions to the HA rules. Have a great day.